Okay, we'll get started. Every group should pick up their report with the written comments. There's just a couple left. And here, this is old stuff that you can pick up if you haven't gotten it yet. So before Chris's guest lecture, we were talking about software patents, which are very much in the news now. And Sarah sent me some articles that she'd noticed in the popular press about this kind of thing. So the interesting problem with software patents, unlike, say, drugs, which are often covered by a single patent, is that a typical design, a computer system, is covered by thousands and thousands of ideas, and each one could theoretically have their own patent about it. So how much of the iPhone's value is a result of the way it scrolls? You know, it sounds like that's a silly thing to be trying to ask, you know, but if, but that's what courts have to do, and that's what some of these lawsuits are about. So, you know, the juries basically end up deciding what they think that particular little bitty feature is worth, and, you know, given that that's what a patent covers. But bringing these patents to court costs millions of dollars. $2 million is a typical amount that you'd expect to spend either enforcing a patent or defending against one. So you can certainly imagine that a little company or even a big company isn't going to want to spend that very often. And you know, so here are some examples. That's an old one back in the I forget when that was, but RIM, the BlackBerry company, was sued by this other company, and they tried to defend it many times and ended up losing in the end, and paid the startup, this other company, $600 million. But the number of patents and the litigations have just skyrocketed. And so this is up to 2010, and you can see the number is 5 to 6 times as many as there were just a couple decades ago. And similarly, the size, the number of patents that have been submitted has skyrocketed, and these are almost all software patents. Software patents are responsible for most of that. This little map shows the number of lawsuits around smartphones. And so we're most familiar with the Apple-Samsung lawsuits because those have been mostly in the news. And some of these other ones have been settled a while ago. So Nokia and Apple had a lot of lawsuits, and then they settled. You'll notice that Microsoft never has any lines with Apple. And as we discussed before, Apple and Microsoft came to an agreement way back in the 90s not to cross-license all their patents and never to sue each other. So that was really beneficial for both parties. But Microsoft is suing other people, Motorola, which is now part of Google, and Sony and so forth, because they do have a lot of really significant software patents around the smartphone thing. And one of you, I forget who it was, brought up the issue of what's called the fair and reasonable patents. So a company, so if you think of a standard like Wi-Fi, right? It's important for Wi-Fi to be a standard so everybody can make their own kinds of routers for it, so every computer can work with Wi-Fi. If it was only one company that worked with Wi-Fi, and, you know, Microsoft laptops worked with Wi-Fi and Apple laptops didn't, and Apple worked with a different kind of wireless network, that would be really bad. And so the standards community got together and said, you know, it's fine if a company has patents around a particular technology that they submit for a standard. So there are a bunch of patents about, you know, networking and so forth that go into Wi-Fi. But there's a rule that all companies, if it's a standard, are required to license their technology for what's called something like fair and reasonable amounts. And it's been a well-established principle in international law and American law, you know, about how much that should be. So if Motorola owns a standard for CDMA, which they do, that's the kind of telephone system we use, they're required to let everybody do it for a reasonable amount of money. So one of the issues with Motorola is, of course, they own a lot of patents because they invented a lot of the basic technologies around phones, around mobile phones. And so now that Google owns them, can they use that patent portfolio to keep other people from doing stuff? And the answer is they're not really supposed to, because they've agreed, as a part of being part of these international standards, that a lot of the low-level technology is required to be licensed at a reasonable value. Now, there aren't any standards around user interface designs, and so none of the interaction technique patents are covered by this. But some of the lawsuits have involved some of this low-level technology that you can claim is standards compliant. So that's something that kind of comes up with patents and software patents, but isn't that relevant to user interface patents. So there's just some recent news about this. This is doesn't have a year, does it? That's kind of annoying. It looks like 2012 that Samsung lost in Europe, and there's a new case in California. So that's these kinds of lawsuits. But there's another kind of lawsuit that's much more in the news, which is when these little companies, which are called non-practicing entities, or sometimes they're called patent assertion entities, which is basically a company that has no business model except owning patents. And so they own a bunch of patents and they try and license or sue people to get them to pay them fees for owning these patents. So when we saw the NTP case before, where they won $600 million from RIM, NTP is one of these assertion things. Now, some of these are companies that tried to make a product and then went bankrupt. So I worked with this little Israeli company on a case that they had a patent on a particular way of creating images, or of using images in their website. And they basically were licensing this technology and these images. And then they claimed that Google and Yahoo and some of the big companies came along and and provided the same service that they were providing without paying them any money, and drove them out of business. And so they ended up becoming just one of these non-practicing entities, because they were driven out of business by the big companies, what they claim stealing their idea. Another example of non-practicing entity is a university, right? So CMU does not make products, and there was this enormous lawsuit that was just in the news, where CMU was supposed to get $1.3 billion from Marvel about these disk drives, and CMU is not making products, right? So we're basically a non-practicing entity or patent assertion entity. But usually these non-practicing entities are called trolls, patent trolls, because, as a pejorative, negative, trolls are supposed to be bad, right? They sit under the bridge and throw people off and stuff like that. Don't let you go by. Don't let you do what you want. So it's kind of the connotation that these patent trolls are evil little companies that only exist to annoy big and little companies. Intellectual Ventures is kind of a large company. It was founded by Nathan Mauerhold, who is one of the founders of Microsoft, with the business model of buying lots and lots of patents. And they have thousands of patents, maybe hundreds of thousands of patents. And they use them to try and license to other companies. They do a little bit of their own research, but almost all of their income comes from licensing. And there's a variety of ways of doing these lawsuits. Typically, they'll be in federal court. So state courts don't get involved in patents because it's a federal law. So almost all of these cases will be in federal courts. And it turns out in the federal court that you can go anywhere you want, pretty much. So the federal court says that if you want to file a lawsuit, it has to be where both companies are doing business. But virtually every big company does business everywhere in the United States. So typically, the person bringing the lawsuit will try to find a court that's very friendly to people who own patents. And there was this judge in a little town in Texas who made it be known that he would be friendly or welcoming of patent lawsuits. And so all these lawsuits went to these little towns in Texas, which became basically famous as places for these kind of lawsuits. And sure enough, it really significantly improved the economy in these little towns because all these rich lawyers would come in and need a place to stay for 3 weeks. And so all the hotels and the restaurants and all the local industries really benefited from this enormous flood of lawsuits of little companies against big companies in these venues. There's a couple other things that happen, though. There's something called the International Trade Commission, which is a very kind of obscure commission or group of judges in Washington, D.C., and they were originally designed to help American companies that had disputes with foreign companies. But it turns out that one of the things they're allowed to do is tell a company they're not allowed to import a product anymore. And one of the reasons they're allowed to tell them that they can't import a product is because they infringe on an American company's patent. And so all of a sudden, a lot of these software patent lawsuits have moved to the ITC because their cases are typically done in 6 months, whereas federal cases are typically done in 3 or 4 years, or maybe even longer. So all of a sudden, you'll see all these cases where the International Trade Commission will be looking to see whether they're going to keep a company from importing a product. And as you can imagine, there's virtually no product made that doesn't have imported parts, at least something. So iPhones, are made in China, based on the design from California. Virtually every product that you might imagine using has at least something that was made somewhere else, in Mexico or China or Singapore or whatever, Canada. So, so that became a particular, and the threat of having your product being embargoed, not allowed to be imported, is a pretty big threat. That's a pretty high bar. You don't want to, not have a product available. And then the newest thing with the patent, the new patent law that was passed in 2000 and something recently, added a new way of re-examining old patents. And so it's become incredibly popular for a company that's getting sued to go to the patent office and say, patent office, you messed up. This patent should not have been issued in the first place. Here's a bunch of new prior art that you should have considered the first time, and why don't you re-examine this patent? And under the new law, that's supposed to be a very quick process, and so that's being used a lot by defendants. So these patent trolls are typically owning or buying these patents, which the reason that people don't like them is most of these patents are really poor quality patents. They're really dopey patents. Often they're written very vaguely, and so it sounds like they cover a whole bunch of different kinds of technologies which other people might believe aren't really appropriate to be patented. And typically they will threaten companies that, you infringe my patent, if you pay me $10,000, I'll go away. And that may seem like a lot of money, but compared to $2 million for defending your product against the patent, obviously it's nothing. So they do this over and over again. And there's, I saw a report that one of these patent trolls sent out 17,000 demand letters to all sorts of companies asking for a fairly small amount of money. And each one, of course, is much more likely to pay up than to be willing to go to court. So you can imagine if you were able to get a reasonable percent of these guys to pay you $10,000, then you've made an awful lot of money without a whole lot of work. So that's considered to be, this big problem. And if you have a little company like, even something as kind of innocuous as a coffee shop that has free Wi-Fi, or anything that any small company that's making anything, you might be a target for one of these companies who claims to have a patent covering something of what you're doing. And litigation by patent trolls is incredibly expensive. It's estimated at least $29 billion in 2011. So that's an awful lot of wasted money on something that's clearly not improving people's creativity. And this has been compared to extortion. You know, if you were the mafia, the classic thing that people said the mafia did was to go to businesses and say, don't you want to buy insurance from me, or to keep your business from being burnt down. And if they didn't do it, then they were at risk of having the mafia burn down their business. So it's kind of the same idea with these trolls. Don't you want to pay me a little bit of money so that you won't get your company sued? And but in this case, unlike the mafia case, it's actually legal to do this. So some of the new laws are trying to curb some of these kinds of practices. So the Electronic Frontier Foundation is very much against patent trolls and this use of the patent system. So this is an email I got just last week. I'm on the EFF's mailing list. So it said, "Dear Brad, it's time to fix our broken patent system, and the Senate's considering much needed changes this very moment, yet powerful interests in pressuring Congress to put the brakes on common sense fixes." So they think these particular fixes are going to help, and they're trying to lobby Congress to pass it. There is a very important case that was heard last week, or a couple weeks ago, in the Supreme Court called Alice Corp versus CLS Bank. And the patent is about a computer-implemented technique for reducing risk in currency and financial transactions. And there's a really there's a lot of discussion about this online. And if the Supreme Court rules in a broad way, they could basically invalidate all software patents. Because one of the questions is this method, this technique, a patentable subject matter? Does it make sense to have a patent on a method for reducing risk in currency and financial transactions? Because remember, patents are not supposed to be about algorithms, and they're not supposed to be about science or ideas. So is the fact that this is a computer-implemented method enough to make it patentable? So in theory, they could have a very broad ruling that would have a dramatic impact on whether software patents are allowed or not. But most people aren't really expecting them to do that. Because companies like Oracle and Microsoft and Apple to a large extent are all significantly dependent on their intellectual property, on their software patents, and so there would be an enormous impact on many companies based on which way they rule. And so the patent industry, the software industry, estimates that collectively there are billions of dollars of value that are being protected by their software patents. So it's an incredibly difficult issue for the courts today. The newest case is Apple versus Samsung in the Northern District of California. The patents in red, so I went and looked at the 5 patents that are at issue in this case, which has just started. It's still going on. And the 4 out of the 5 patents are interaction techniques. So it really is about the stuff we've been talking about in class. The top one, system and method for performing an action on a structure in a computer-generated data. The pictures in the patent show this concept that you see on iPhones, where if you select some text and click on it, you get a menu or an option of doing things like calling that number. Right? So that's what this first patent seems to be about. The second patent, universal interface for retrieving information in a computer system. The figure has this text field, and you type some text in there, and it tries to figure out what to do with that based on the current context. The next one seems to be more about operating system synchronization stuff, so it doesn't seem to be about user interface-y kind of things. So basically, I didn't read these in depth. I was just skimming them to see. And you're certainly, it's easy enough to go onto Google these days and see the full text of the patents and decide for yourself if they're user interfaces. Method, system, and graphical user interface for providing word recommendations. Unlocking a device by performing a gesture on an unlock image. And this is the image. You can certainly recognize what that seems to be like. And that's a patented feature of iPhones that seems to be covered by this patent. So the Samsung is countersuing with a couple of patents that didn't seem to be particularly user interfacey, but in any case, you can certainly see how this multi-million-dollar, if not billion-dollar lawsuit is going to revolve around interaction techniques that we've been talking about. So it'll be really interesting to see where everything goes on that. All right, I guess we'll just stop this. So you may be interested in when we did the survey, the homeworks, which is quiz 7, that in terms of the class, 24 people filled out the quiz, and of those 9 were against software patents and 15 were in favor of it. At the time, probably my lecture was mostly arguing in favor, so it'll be interesting to see if everyone still agrees with the same positions. Everybody got a 10 who filled this out. Everyone had some really interesting arguments about for and against patents. All seemed very valid, so didn't take off any points for anybody based on their opinion. And I'm really personally, you know, kind of understand both sides of this. You know, as an inventor, I really appreciate the ability to get a patent on things that I invent. And as a consultant, I see an awful lot of really bad patents that should definitely not have been issued. Okay, everyone should pick up their homework evaluations and the old quizzes. So we have 2 sections next week for everybody to present their results. So that's 80 minutes per lecture. I figure if everyone takes 12 minutes plus 3 minutes, that would be 15 minutes. And if we put 5 talks in the first one, that'll be 75 minutes, which will just barely fit into 80 minutes. So everyone should practice. You should make sure your talk is about the right length. I'm going to definitely cut you off at 15 minutes, and we'll dock you a few points if you go over 12 minutes, or if you're dramatically too short. I'm sure you have plenty to say, and if you just go for 8 minutes, it'll look like you didn't practice and didn't know what you were going to be talking about. So make sure that you're between 10 and 12 minutes for your presentations. And also, you know, this room is pretty easy to get into. You should practice and make sure your laptop, whichever one you're using, works, and that you know how to make it project onto the screen. There isn't a Mac plug here, so if you just have a Mac, bring your own adapter. And make sure that you got you know, everything you need to make it work.
Does that have HDMI or is it just VGA?
Just VGA. Yeah, that's all we have in here. Yep. Nope. Nothing else. And if you want to, if you just want to use PDF and you want to email me your PDF, that's fine. You can project from my laptop. 5?
You can use my computer too.
Well, it's also a PC, right?
Yeah.
Yeah. Right. Yeah. If we both of us have PCs, so if you're using a Mac and you don't have the right stuff, I can't really deal with Keynote. And if you have a PowerPoint that you made on a Mac, often it gets messed up with fonts and stuff if you use it on a PC without change. So PDFs usually work really well. If you want to give a demo and that kind of thing, make sure you find an adapter for some. Who has Mac adapters for VGA? Not many people. Do you have one?
I have it on my Mac.
For what kind of Mac?
Newer one.
Okay. So you can check with Buck and see if he has the right adapters for your laptop. So it'll be, we'll definitely be counting against you if you're not ready to go when it's your turn. And I'll be posting the order before Wednesday. And we decided just to do it randomly and to let people know. Okay, so today's topic is about implementation techniques, and I know at least half of you guys are not computer science background, so I tried to make this general and not, so it won't be boring to computer science people being redundant, and it won't be completely unintelligible to people who aren't. So that's quite a challenging task, but hopefully I will be telling you stuff that is useful. And basically the idea is how would you implement some of the kinds of techniques that we were talking about? And what is the current state of the art? How did it get there? And what is the current research in implementation techniques? So it turns out that implementing interaction techniques is not too much different than implementing the rest of the user interface, but there are some subtle differences. So some of the stuff I'm going to say applies to implementing the interface in general, and some of it's really very focused on implementing interaction techniques specifically. It's actually been a significant area of research, how to do this implementation. There's a long-running conference called the User Interface Software and Technology Conference, UIST, whose deadline is actually Wednesday, and so all the people upstairs are going crazy trying to get their papers done by Wednesday night for this conference. And one of its focuses over the years has been the software, how you implement all of these user interfaces. And it turns out that a lot of the ideas that everybody uses today in terms of toolkits and interactive tools that we'll be talking about were actually invented by researchers, including my research group, over many years. If you're interested in this, obviously it's covered pretty well, mostly in SAWI. How many people took SAWI here? Anybody? 2? Okay. How many people took PUI? So PUI is much lighter weight. What did you use when you took PUI? Did you use Python or JavaScript? Flex? Yeah, so Flash, ActionScript from Adobe. So in SAWI, I guess you guys use Java?
There was a weblog tool that used JavaScript.
Yeah, so Java or JavaScript. So those are, kind of languages or toolkits that are designed to help you build user interfaces in general. But neither of them really talks about how to implement new interaction techniques. It's mostly about using interaction techniques. Then I offer a course periodically in the spring called Advanced User Interface Software, which is very specifically about how to implement toolkits themselves. And so that's something that's available occasionally. So what are the different layers? At the bottom layer, we'll have the operating system. On top of that, there's something called the window system, window manager, then the toolkits, and then higher level tools, and then you've got your application. And we'll go over each of these layers in detail. So the lowest level, the operating system, I'm sure you've heard that term. That would be what you would call Microsoft Windows as an operating system, or the Macintosh OS. OS stands for operating system. iOS, I guess, originally stood for the iPhone operating system, which is slightly different than the Macintosh operating system. Android is another operating system, which is built on top of Linux, which is another operating system. So all of these are names of operating systems, and they all have fairly similar roles, fairly similar sets of things that they provide to programmers and to users, but they're fairly different architectures underneath. In the old days, remember we saw Smalltalk and we saw the Xerox Star. All of those would have had custom operating systems that they were built on, Bravo. And so those were very much harder back in those days because there was much less available in terms of software in order to build on top of. So what does the operating system do? Well, first of all, it has to handle the hardware. So when you push your finger down on a keyboard key, that's a hardware event. A switch closes and something happens at a very low level, and there's a whole bunch of software that has to figure out, oh, that was the E key, and figure out what the ASCII value is for that, and whether the shift key is down at the same time, and generate the event that eventually comes up to the user. And if you go like this and hit a whole bunch of keys at once, then some piece of software has to linearize that and put them in an order and deal with the fact that a bunch of stuff happened at basically the same time. And similarly, there's a microphone, there's speakers, there's the USB port when you plug your mouse in, And so all these what are called device drivers, really low-level software, is handled by the operating system. So that's the input. And then also for the output, when your software wants to draw a circle, some layer of software is going to say what pixels go on. But then there's a device driver that says, oh, if this pixel is supposed to be green, then let me go tell the hardware to actually paint it green when it's appropriate. So that's the user interface stuff that the operating system does. But it's also responsible for a whole bunch of other stuff that we don't really care about, like the file system, like networking, pretty much all of the interface between your computer and the outside world. The operating system itself is written in some language, typically C++, although Android is mostly in Java. But that doesn't mean that you have to actually call that same API, although you can if you want. But typically, there'll be libraries that provide exactly the same functionality in a more convenient way. And so if you're writing in Java, there are a whole bunch of libraries, over 3,000 libraries in Java, 3,000 classes, that provide the same functionality as the operating system. So in Java, you can look at the files. And in Java, you can go to the network. And in Java, you can access the low-level keyboard keys and so forth. And those libraries basically provide what's called a wrapper around the operating system functionality. And the same thing's available in JavaScript and in Flex and so forth that give you everything you need to be able to do in the same way the operating system does. The next level is the windowing system. So if you were writing a high-performance game, you might take over the whole screen and also the keyboard and work really low level at the operating system level of saying, I'm just going to take over the screen. I'm just going to take the keys directly and try and get maximum performance. But most of the time, and when you're doing anything user interfacey, you're going to want to deal with the window manager. And that's which obviously divides the screen into little sections and also decides which application should be getting the input when multiple ones are running at the same time. So even in the iPhone and Android, you have multiple applications running at the same time. Only one of them's on the screen. That's the one getting the input. It's the window manager that's in charge of that. And the window manager also provides the user interface that lets you decide which window is on the front, change the window size, all that kind of stuff. The user interface that we talked about in the user interface when we talked about window managers is all provided there as well. And then the next level up are the toolkits. And this is a library. This is where the widgets finally come in. So the interaction techniques like menus and scroll bars and text input fields are in a library that's usually called the user interface toolkit or toolkit. And the toolkit level is the programming interface to all of these widgets. So if you're a programmer and you want a menu, then you'd use the toolkit to use the built-in menu from the system. And typically, if you're on Windows, you would use the built-in Windows menu. But it turns out that like Java with Swing, the Java Swing package ignores the menus that are built into Windows and re-implements them from scratch in Java using the really low-level windowing system calls. So why would Java ignore these perfectly good menus that are built into Windows and provide their own implementation? Yeah?
Because it will work across all the operating systems.
Right. So the main reason is that Java also works on Linux and it also works on the Macintosh. And those windowing systems, those toolkits work quite differently. So the menus on the Macintosh are quite different than the menus on Windows and different than ones on Linux. And so Java Swing can say, OK, that's too much trouble. I'll just implement my own menus, and then every Java application will work the same across all platforms. So the same thing's done in JavaScript. If you're trying to write a browser application and you want to use menus, none of the menus you're going to use are going to be the built-in ones from the operating system. They'd all be custom ones. What's another advantage of re-implementing them in the programming language besides the portability? Yeah?
Well, if the programmer is familiar with that language and it's implemented in that language, they could change it to their own needs.
Right, so you can customize them more easily, right? If you're calling out to the Windows menu system, there's no way from Java you're going to be able to make a slightly variant of menus or something that works slightly differently. But if you're using this built-in or this mechanism in your language, then you can make customization. So that's another good reason. Yeah?
You can take advantage of language features that aren't available in C, which is what the OS probably is right now.
Right. So one of the nice things about Java, it's object-oriented, has inheritance, and so the design for the connection to how you would use menus can be very consistent with the way you're used to programming in Java. Whereas if you're trying to call out to a C++ menu system, you'll have to have all these hacks around to try and deal with the very different ways that the underlying system wants you to talk to its menus compared to the way the language does. So there are lots of good reasons to re-implement it. But on the other hand, there are lots of toolkits that don't re-implement and use it, like Java's SWT toolkit that comes with Eclipse, actually calls out to the low-level toolkits. Why might you want to do that instead? So not re-implement them, but instead use the underlying toolkits and just kind of put a wrapper on top of it. Go ahead. Right, so it's much more likely that it'll be a consistent look and feel. So if you're doing a Macintosh application in Java and you go from, I don't know, Adobe Illustrator in the Macintosh to this Java application you just built, the menus will operate the same way as everyone's used to on the Macintosh because it is that underlying implementation.
It's also likely to be faster.
And it'll be a lot faster, yeah. To the extent that you have any speed issues, which isn't really so relevant anymore, but used to be much more significant, using the underlying system will be more efficient. And another one that's closely related to the first one is that there are all these special mechanisms that are built into a lot of these, like the keyboard accelerators and and all those will work in the standard way that you may be used to. Also, things like assistive technologies. If you try to turn on screen reading or techniques for adapting the menus or the other widgets for somebody who's handicapped, all that will work in the expected ways. So there's this big trade-off between whether to re-implement the toolkits or use the low-level ones. So there's some standard toolkits, the Macintosh toolbox, the Windows toolkit. There's the Java Swing one. In HTML, you've got a few widgets built in. So there's links, obviously, text input fields, buttons, and so forth in HTML that are defined, those widgets. They're called input controls. Obviously, for output, you've got the DOM, all the HTML5 kind of things. There are also a bunch of libraries. So the jQuery library in JavaScript has a bunch of nice widgets and pop-ups and all sorts of useful things if you wanted to use those in JavaScript. And then there's been a whole bunch of research systems, and I'll show you some of the ones that have come out of my lab. So the toolkits is a way of collecting together all of these low-level interaction techniques that we've been talking about in this whole class. And the advantages of using this toolkit are pretty obvious that, like we said, it helps maintain consistency. So we talked a lot about the innovations in the Xerox Star and the Apple Macintosh. One of the key innovations we haven't actually talked about is the toolkit. So when the Star came out, of course, they didn't have very many third-party applications. But when the Macintosh came out and the Lisa, they definitely expected third parties to make most of the applications for those systems. And the PCs and the Atari and all the computers that had been out before that it was basically a free-for-all. Everyone could make up whatever kind of interfaces they wanted. One of the key features of the Macintosh was the Macintosh style guidelines, which said, if you're going to write a Macintosh application, here is what you should do. You should have an edit menu, and the items in the edit menu should be this. And if you do the word, if you have an operation called copy, here's what it has to do. And you remember the star had a copy that did something entirely different, right? So the Macintosh was very innovative in having these guidelines. It was a very long book that basically told you as a designer how you were supposed to design your interface. And making that, just telling people they had to do that was, that was useful, but it wouldn't probably have worked if that's all they had done. So in order to make it possible for people to follow those rules, they provided this toolkit that helped the programmer actually do it the right way. And they had all these extra information for programmers about how to use the toolkit, and eventually they made it simpler. The original version was kind of tricky to use in the right way, but it got better. But the general idea was that as a developer, the path of least resistance, or the easiest way to make a Macintosh application, was to follow the rules, was to use the built-in toolkit in the standard way and be consistent with everything else. And so that really had a big impact on the ability of developers then to make things Macintosh compliant. And we talked about how Windows was available around the same time. Microsoft Windows really did not have a toolkit for quite a while. They didn't have this style guidelines for many years. And so one of the really important innovations of the Macintosh was having this toolkit and the ability for programmers to follow the rules. And it provided these common features that pretty much every application needed. How to do menus, how to do scrolling, and so forth. So the next level up, where did our little chart go? So the next level up after toolkits are vaguely called higher level tools. Not very helpful name. These are typically graphical tools where you can use a mouse to do part of the interface design. So we're all used to those kinds of tools today. We use them all the time. Things like Balsamiq or interface builders. You might use Photoshop or Illustrator to do a prototype. You might use Resource Editor to lay out where you want your widgets go, or an editor like Dreamweaver. But all of those tools have predecessors in research and in early systems. So for example, Menulay, and I think I have more on that later, was invented by Bill Buxton at the University of Toronto as an interactive tool in '83. The Trillium was a tool for actually laying out panels for Xerox copiers. So if you think of a copier nowadays, it has a little computer screen with a touch panel for most of the interface instead of physical buttons. And so they invented this technique for prototyping those. And then, a lot of the stuff we've been talking about are how individuals had a big influence on what happened. And so this guy, Jean-Marie Hulot, a French guy, was working in INRIA, which is a French national laboratory for computer science. And he was working in Lisp, and he built himself an interface builder based on some of this early research in order to make it easier to build user interfaces in Lisp. And Steve Jobs hired him away from INRIA to work at Next, and and Jean-Marie created this interface builder, which was one of the central parts of the Next user interface toolkit. And so then designers who were designing for the Next could actually draw out a lot of their user interfaces, and so it was much easier to build interfaces for the Next than it had been for the Macintosh or Windows of the time. So that got to be really important, and it was immediately copied by lots of other people and lots of other systems. And so nowadays we can't really imagine building a user interface without having these graphical tools. But a lot of it can be traced back to the fact that Steve Jobs hired this guy away from INRIA. So they're run by various names: interface builders, layout tools, resource editors, prototyping tools. The idea is that, without these, if you wanted to figure out what color something would be, you'd have to write code to try out a color, and you wouldn't be able to try out very many of them very quickly. Or if you wanted to adjust the location, you would have to write code to do that. It makes a lot more sense to be able to do those kind of things interactively, to be able to just adjust the layouts of objects to put them where you want them, to figure out what color you want interactively. The other important advantage is that it's accessible to non-programmers. So if you have a graphic designer on your team who's really good at picking colors and layouts and making things look attractive, it's much better if they can actually do the design in the tool rather than having to draw it on paper and tell the programmer to do it. Or try and do it in Photoshop and then have the programmer repeat it. So the idea of these tools is that those kind of people then can do it themselves directly. So there are kind of two classes of these tools. There's the interface builders that create the interface for real, and then there are prototyping tools that just create prototypes. So these just show storyboards of what the screens will look like. Sometimes they're called click-through prototypes. Hopefully, has everybody who has used some tool like this for creating interfaces or prototypes? Anybody? So creating simulations. How many people have used Dreamweaver? Okay, a few more people. So Dreamweaver is often used actually to make prototypes, but it's also obviously used to make real websites. So in all of these tools, you can do some behaviors without writing code. So in Dreamweaver, it's easy to make it go to the next page. That's really easy. In most of these click-through tools, you can click on things and make them go to the next page, kind of exactly the same way as you can do in Dreamweaver. And the goal is that you can just sketch out the interfaces really quickly. Sometimes what you're doing is just a painting, and there's no way to really convert it into real code. And other times there's some way to do that. Typically, they don't use the real widgets. So if you're prototyping a Macintosh interface, you might have file, edit, etc. across the top, but they're not the real version that will be used on the Macintosh. You have to reprogram them later. And that's why these are called low-fidelity prototypes, because they really aren't the same thing as the interfaces that will be really used. It turns out that these prototyping tools actually have a really long history too. So Dan Bricklin, who is the inventor of VisiCalc, the original spreadsheet, so he way before this had invented VisiCalc, the spreadsheet program originally for like the Apple II or something like that, even before there was the Macintosh and Windows. Had a fairly successful company for a while and was getting frustrated at how hard it was to figure out what interfaces should look like. And so he built this DOS tool called Demo that would let you interactively say what DOS interfaces would look like. And if you remember DOS interfaces, that's just characters, right? And so a screen, you could move your cursor, use the mouse or your keyboard keys to move your cursor any place and plop down some characters any place on the screen you wanted. And then you could define some simple behaviors like going to the next screen or so forth. And so this is way back in '85. Eventually, Bill Atkinson, who was one of the key designers of the Macintosh and did Mac Paint, was getting frustrated with how hard it was to program and invented HyperCard. I think, did we talk about HyperCard before? I think we did. And that was in '87. And HyperCard, he didn't really want it to be a prototyping environment, but that turned out to be one of its key uses. Millions of people around the world found that HyperCard was a really good way of prototyping interfaces that they then would go and back and re-implement for real in a regular way. So these prototyping tool idea goes way back into the 80s, just like a lot of the interaction techniques that we've been talking about. So modern examples, who's used some of these kind of tools? Mockups, Balsamic, Acture, Envision. Anybody used any of these? Yeah, a few people. So these are really cool web-based tools that let you just draw out really quickly examples of an interface. And you can basically, they typically have menus. So these are all pretend. These are just pictures. They're all pretend interactions. And so you can drag this screeny thing into your interface and say, let's pretend this is going to be an iPhone app. And then you can drag, number things in or keyboards. And they're just pictures. And you can then say, when I click here, then I want, something to happen. Or when I click here, then add this checkbox and so forth. And so the idea is that you can quickly show a simulation of at least one path through the user interface, if not a few different paths. It's very effective for testing out your ideas and quickly prototyping what the interface should look like. And the other end of the spectrum are interface builders that are designed to build parts of the real interface. And so an interface builder, which is sometimes called an interface development tool or a GUI builder or resource editors, all of these are designed to be part of the real implementation. So these never do the whole implementation, but they're also not for prototyping. They're building the real thing. And so almost all interface builders are designed to help you use the interaction techniques that are in the toolkit. So it's going to have a big palette like this, listing all of the built-in interaction techniques. And then you basically pick the interaction techniques you want, and you put them into the window, and you define properties to them, and then you pass it over to the programmer who writes the code that says what actually happens when you click on these buttons. And so it's all about doing the layout and the properties, like what colors things are, what are the actual strings that go into the widgets and so forth. Where are the dialog boxes? So it's basically organizing, laying out, and selecting the widgets on your screen. There are typically a whole bunch of properties for widgets. It's amazing how many parameters modern widgets have. So if you look at like something as simple as a button on Windows or the Macintosh, it may have 30 different parameters. It's like how could you possibly have so many different options? But if you think about all the different colors and all the states it can be in, remember all those modes we did, each one of it might have its own different behavior and descriptions, the fonts, how things change, and so forth. So there's lots and lots of parameters that can be set in these editors. So you put them all out. If there's anything that changes dynamically in your application, then you just put a rectangle and let the programmer deal with that part. So these interface builders generally don't let you do much about anything that's dynamic in your program except for say where it goes. So the result is that they're pretty easy to use. They're very important and an important part of the development process for most products, but they are pretty limited. And then in order to get them to do anything, you put code behind each of the buttons or scroll bars or text input fields. And those are called callbacks because it calls back into your code, right? So that sometimes they're called event handlers, but it's basically the same idea that when the user uses this interaction technique, then something should happen in your interface in the back end, and that's has to be written as a callback. So a lot of interface builders, like a Visual Basic, when you put a button somewhere, it's at some number. like 37 pixels across. And so that's really simple. You know, if I drag this button to be right here, then it can, and I click on this button, it'll say, oh, this is a pixel number 100 by 300, and it obviously will just stay at that particular position. But it turns out that's almost always not what you want. You typically don't want things at a particular value because sometimes things change in runtime. So one of the things that changes is what language you're using. So you often want an interface to be able to work in English and in French, or in Chinese, or in Hebrew. And then all the things have to be in different places. So if things are always at 100, 100, then that's harder to do. You also may want things to change size dynamically if the user changes the screen resolution or changes the size of the window, or if there's something else that appears dynamically at runtime. And so one of the things that's available in a lot of these tools is a way to say how these things should be laid out at a more abstract level. So you might say, this should be in a row, or these should be in a column, or this should be next to this other thing. And so having these relative layouts, these layouts that depend on what's already there or depend on each other, is a really important aspect to a lot of these toolkits. And it makes it a lot more complicated for the programmer or for the designer to say where everything goes. You can, if you've ever done this in HTML, how many people have created a page in HTML? Hopefully most people. You can't actually say, or at least until divs in HTML5, you couldn't say that something was at a particular pixel location. Right? If you wanted a nice layout, typically you would just start at the top and lay things out, and the system would figure out where things go for you. You could try and use tables to put things side by side, which was always a little awkward. And there were a few other things you could say, like this picture should be to the right and things like that. With divs, now you can actually say they go at a particular pixel location, but it's still a little tricky to make that work out. So this idea of having layouts, of having the system figure out where things go, and the developer has to compute these layout constraints is a tricky thing that's been added. Another thing that makes these more complicated is this idea of resources. So we talked about this idea of internationalizing or translating interfaces. And most of the time in your code, if you're Apple or some company that's writing an application, Adobe, that's supposed to be used all over the world, it would be great if your programmers didn't have to reprogram your interface for every language that needs to be converted into. And so there's this idea that the programmer should be able to refer to things like a button by some name that's going to work in any language. So if I say OK, the OK button, and then I translate this into Chinese or something where it's not called the OK button, then how am I going to find it or make that same code work in different languages? And so the idea of a resource is that instead of having a button called OK, I have a button that has some ID number, 37. So button 37 is OK, and somewhere there's a file that says in English 37 uses the string OK. And in Portuguese it uses some other string, or in Chinese it uses some other string. And so by having this indirection, the code then doesn't have to change as you're changing what language the interface is written in. And so you can imagine there's lots of things that once you put the strings in, then the size of the button now is changing. Right? So in English, things are pretty small. In French, things are 30% larger. German tends to be larger. Anybody's language smaller than English? Chinese. Chinese interfaces, are things closer together than English interfaces? I'm not sure they're actually smaller.
Words should at least literally be.
Yeah.
Because it's fewer glyphs.
Yeah. What?
Arabic
Arabic and Hebrew are right to left. Chinese is up and down. Is that right? Mm-hmm. It's right to left. Left to right. Yeah, mostly left to right. But I don't think it's actually smaller. But there are definitely languages that are bigger. French is almost always bigger than English. So it's not sufficient just to have the string OK in your language, in your resource file. You also have to have the positions of all the widgets. And those have to be redesigned based on the particular language. And other things like colors. Red is a warning in English, but in other cultures, red might not be a good color to use for warnings and so forth. So the general idea is that you take this file and put everything into it that could change in a different language, and then the programmer just deals with these abstract numbers, and then it's easier to translate. That makes it a little harder for the interface builders, because now everything has to be done through this level of indirection. Typically, an interface builder doesn't supply any support for lots of stuff, like error checking, graying out of widgets when they're disabled, default values, any widgets that change dynamically at runtime, visibility, like if you have cards or tabs and you want those to come and go, and kind of anything that's created dynamically at runtime. So typically the interface designer would kind of say where these widgets go, and then it would be up to the programmers writing the code behind the scenes to deal with all of these dynamic properties. So I mentioned Menulay, which was this really early interface builder. And this was, remember we talked about vector screens and the light pens. And so this was done before the mouse, 83. And so it's kind of a funny video. Let's see if we can play it.
Increasingly, graphical input and output techniques are being combined in order to construct powerful, interactive user interfaces. In the program being demonstrated, the operator is using a number of techniques in order to design a flowchart. The example shows how both hands and various devices can be combined to make use of the operator's full operating potential. Such interfaces are hard to construct, however. In this tape, we will demonstrate two tools developed at the University of Toronto in order to facilitate this task. The first is a runtime support package that handles user interaction. It is a table-driven package that handles all input, event detection, screen updates, and procedure invocation. Even on its own, such a tool frees applications programmers from low-level detail, facilitates software maintenance by enforcing a common programming methodology for user interfaces, and finally, it facilitates portability of application software, since all interaction is via a standard software package. This next example is a simple chemistry simulation on titration. Adding acid brings a solution to equivalence. Acid is added by pushing the tablet selection button while pointing at the burette. Equivalence is indicated by a color change in the beaker and the sound effect. Let's reconstruct this simple program as a means of illustrating our second main tool, Menulay. Menulay is a program for interactively designing the user interface software. It is a preprocessor whose output is automatically translated into high-level source code. Menulay generated itself, so all interactions used in working through our example are available candidates for our titration experiment. Our first step is to draw the objects which are to appear on the display. Here, a simple sketch editor is being used to draw the burette. Our step is to design the layout for our display. First, we select and position the graphical elements to be employed. We use our hand-drawn objects, all of which are immediately available through the picture library at the bottom of the screen. We then add the necessary text by positioning the tracking symbol and typing on the keyboard. We then assign colors to the objects. Since we're using a monochrome terminal, colors appear as words. They will be properly displayed when shown on the final device. Next, we will specify the semantics of the experiment. We do this by typing the names of the procedures to be associated with each active object. The procedures must be pre- or post-defined by the applications programmer, or defined on the spot within Menulay. Nearing the end, we will now do the final scaling and positioning of objects. Note that in positioning objects, we can make use of a grid for increased accuracy.
So all these things like gridding and typing on the keyboard and all this stuff sounds so old-fashioned or commonplace today, but this was pretty much the first system that demonstrated any of these kind of techniques. So that's kind of why he's explaining it. Nowadays, you'd never mention, oh, and you can type, because that would seem kind of silly to even mention that. But this is when these ideas started.
Having finished our specification, we now save our work. We are ready to invoke the process specification into C code, compile the result, and link it with our runtime support package. In doing so, all options are selectable by the menu. We now exit Menulay and are ready to run Play.
Okay, so that was a pretty revolutionary system, demonstrated at SIGGRAPH, a big graphics conference in '83, showing how you could do all these things interactively. As we mentioned, the Next Interface Builder really popularized the name. Jean-Marie, I think, came up with the name Interface Builder, and Next really took advantage of that. Visual Basic was one of the early adopters of this technology and made the use of an interface builder a key part of the user interface. That's where the visual part comes from. A lot of people thought it was a visual language. It's not really a visual programming language. Instead, it's a visual editor, an interface builder, coupled with using BASIC for the backend. So this is a Visual Basic screen from a previous version. This is visualbasic.net. So there's all sorts of things you're seeing here. Here's the palette. So checkboxes, panels, pictures, buttons. So there's a really long list of widgets, and there's way more than you can see here. There's more panels. This is the interface itself that we're creating. So there are these groups and some buttons. This is the code that goes with stuff so that you can actually type the Visual Basic code right into the window here if you want, or you can send it off to somebody else to do it for you. And then over here is a property sheet. And it has this long list of properties of whatever you selected, the size, the color, a whole bunch of things that control how it behaves and so forth. And then various ways of navigating. Okay, so those are kind of the various levels of tools. And I want to just talk about another topic, how the software is typically organized. There's a term that often is used that's really relevant to user interface design and interaction design. So this is kind of what you might call a software model or an architecture. You might have heard of the term interface architecture or information architecture. This is the same kind of thing for the software. Basically, it's how you might organize all the code that you have to write. And the general goal is to try and make it easier for the programmers to work separately from the user interface designers. So ideally, you could have the programmers go off and implement your application at the same time the user interface designers are trying to figure out what it looks like and how it should behave. And so you can do iterative user studies and all these kind of things at the same time the developers are working. No one's really figured out a way of achieving that entirely, but a lot of these architectures help with that to some extent. And the key architecture that seemed important to talk to you guys about that's relevant to widgets, to interaction techniques, is called the model view controller architecture, which was invented by Smalltalk around 1980. And they talked about it a lot, but they never really wrote anything about it. And a lot of people talk about it, but there's really very little discussion about how it's really supposed to be done. And what part of it, what part goes in the model, what part goes in the view, what part goes in the controller. It seems like a pretty straightforward idea. The model is kind of the information behind the scenes. So for a scroll bar, a model would just be a number, like 20%. And that would tell you what part of the file you're looking at. For a text input field, the model would just be the text. What did the user enter? For a button, the model would just be checked or, clicked or not clicked, or something simple like that. So the model is usually pretty simple for interaction techniques. The view is what it looks like on the screen. And then the controller is how the user operates it with the keyboard and mouse. So it sounds pretty straightforward in principle. It turns out, however, it's really hard to carry through in practice. And typically, the way it's supposed to work is that when you program a new model, then you can use that model with a variety of views. And similarly, if you have a single model, you can have all these different views as ways of looking at it. So here's a picture. So there's one model, which is a number, and you can use some kind of slider or scroll bar to let you input that number, but you could also use a text field, right, and let people type the number. And you could even have it be output only. This is supposed to be a visualization where the user can't interact with it, but maybe it's a progress bar or a thermometer or something. It's just showing you the number, but you're not allowed to edit it. And so the idea is that you can have that one model that keeps track of this number and lots of different views and controllers that would let the user see and edit it. And one of the things that turns out to be kind of tricky is whether you can, if you have a new view, almost always a view has to have its own controller, right? So the controller that deals with text input has to know a lot about what the text input field looks like. And the view that deals with letting you click on the slider and moving it back and forth has to know a lot about what the slider looks like. So it turns out in practice, the controller and the view are very tightly coupled. And the code that runs one has to really know about the other. And typically when we think of widgets and interaction techniques, it's a combination of these two together, right? And so if you're inventing your own new kind of scroll bar or a gesture or whatever, you're going to think about the feedback and what it looks like on the screen and the pictures, as well as what the user is supposed to do with it. So the user operates the input device. That changes the value. Oops. And the controller is going to notify the model that its value should change, and that should then tell everybody who's looking at it. So in practice, it turns out this is kind of tricky to organize, to understand how different controllers and views should be architected, should be written, what part of the code goes into each part. And also another interesting thing is that to the extent that you try and follow this model view controller idea and you want to add something new to your interface, typically you have to write little pieces of code in lots of different places. So, or if you want to modify the way things work. So if you have an interface where you have, say this model and this view, and then you decide, okay, now we need two different numbers. We need 3, 4, 5, plus we need this other number for this other part of it. Then you'll have to write some new code in the model part of the code, and you'll have to write some new code in the controller part of the code, and new code in the view part of the control code. And so you end up having your code distributed in all different places, which turns out to make it really hard to modify later when you change your mind again, and to do the kind of iterative design that we recommend. And also a lot of these controllers, a lot of these systems have parts, right? So, it's pretty simple if you just have a single number, but if this is a dialog box about a font, there are all these things about fonts. There's the font size, the font color, which particular face you're using, whether it's italics or bold. So now you've got all these different pieces that you're putting together, and maybe the model is the font object, and that's what goes over here. But now your controller isn't just one widget like a text input field, but a whole collection of maybe 10 widgets that give you all the different parts of the font value. Or you can imagine lots of other situations where, if you're picking a movie, what's the movie name, what's the movie time, all the different properties that you would need to pick have to be somehow combined. And so the idea that, well, you have a model, sounded pretty simple in practice, but now my model has all these pieces, and is there a view controller for each piece or a view controller for the top level? So it turns out in practice it's not quite as easy as it seemed like it should be. So there's been a whole bunch of research, as I mentioned, on how to design these toolkits and interactive tools over the years. And I'm happy to say that I did a lot of this original research quite a long time ago. So as soon as I came to CMU in 1987, I started working on a toolkit called Garnet, which is a silly acronym, and worked in Lisp for 7 years. Lisp, who's heard of Lisp? Oh, most people. So Lisp was an early programming language invented probably in the 60s at Stanford by McCarthy as an AI language. It has a lot of the advantages of JavaScript. It's a really dynamic language. For the time, it ran fairly quickly. It made it fairly easy to build experimental programs in. Eventually, it died out. Anybody ever programmed in Lisp? Yeah, OK. So very few people have ever used it. But it was a lot of fun. I really enjoyed programming Lisp. Then it went out of favor. And the military, who was funding the research at the time, said they didn't like Lisp anymore. And so I had to redo a lot of the stuff in C++ in a system called Amulet, which is a different silly acronym. And Amulet's like a necklace, a little charm that you could wear around your neck, whereas Garnet is actually a gemstone. So they had the same architecture and very similar low-level tools. And I think I'll go through this architecture and then stop. So this picture is very similar to the one that we saw before, where you have kind of the operating system down here, and then kind of the window manager level stuff. And then we added a bunch of new layers on top of that. So one of the things to notice is that the widgets are way up here, and there's all this stuff in the middle. And the goal of Amulet and Garnet was to try and make it easier to build new interaction techniques. So nowadays, the three groups that are trying to build interaction techniques, two or three groups, are having to write it in JavaScript, ignoring the menus and so forth. And the idea of the constraint system and the interactors was to make it so that that was a lot easier to do, that you could build your own widgets. And then we talked about interface builders, and we did a lot of the really interesting early work on how those should work. I think I changed my mind, because this is a reasonable length video, so I think we'll wait and do that next time on Wednesday. So most of Wednesday, well, we can't run. The lecture has to stop at the end of Wednesday because you guys are presenting next week, and then I'm out of town. So I probably will spend more time on this and just a little bit of time on AI interfaces, intelligent interfaces. So we can definitely finish with the lecture content by the end of Wednesday. But I'll pick up here next time. Don't forget to get your comments on your interim documents. It's important to take those into account and pick up all homework so you don't have to keep them.